All right. Thanks for coming here. Middle of the weekend, convocation, family weekend, all of that. So, where I left off last time was in talking about the phase transformations. Well, the phase is actually of water, the chemical, which consists of what we call ice, what we call water, or just water, the liquid, and what we call the gaseous form that we call steam or water vapor. So the transformations between those phases, the phases themselves, some questions that I've just been talking about. When you relevant to this, when you add heat to something, in general you increase its temperature. That is, you've got just a piece of aluminum, and it's at room temperature, and you add heat to it, which is to say you let thermal energy flow from a hotter object to that colder piece of aluminum. The temperature of the aluminum goes up. And the reason I use the word general is because there's an important exception, and that's what we're dealing with right now. And that is that the heat normally causes the temperature to go up, but it can also cause a phase transformation. And often during a phase transformation, the addition of heat doesn't increase the temperature, it simply drives the phase transformation. And that's the case with ice melting into water. If you have a piece of ice and you make it very cold, as I showed you last time, make it very cold, it's just like any other normal solid material. When you add heat to it, its temperature goes up. But once it hits 32 Fahrenheit or 0 Celsius, that added heat stops increasing the temperature. It's still going into the material, it's still increasing the overall energy of the material, but what it's doing is instead of increasing the average thermal kinetic energy of the particles, which is to say increasing their temperature, it goes into paying the energy cost of melting the ice. It takes energy to free up the water molecules from one another enough that they go from being rigidly arranged in ice, which is a crystalline material. You occasionally see the crystals mostly in the form of frost on windows in winter. You can see that it's got crystal facets. Normal ice, you don't see the crystal facets, but it is a crystal. So when you put energy into ice at 32 Fahrenheit, it begins to melt. You're paying the cost of freeing up the atoms, the molecules, from their crystalline form and allowing them to move around relative to each other, to flow. The liquid flows. The molecules in a liquid are still in contact with one another, but they have much more mobility than they have in the solid, and so they move around. And that takes energy. It takes a considerable amount of energy, actually, to melt ice, even without raising its temperature. That energy that's required to take ice at 32 Fahrenheit and turn it into liquid water at 32 Fahrenheit is called the latent heat of, I call it latent heat of melting. It's officially latent heat of fusion. Again, it doesn't. What's fusion? It's a fancy name for melting. Questions about that idea? Similarly, when you go the other direction, when you begin to take heat out of liquid water, if it's at room temperature, you take heat out of it by letting the heat flow to a colder something, maybe your refrigerator, your freezer. The heat's flowing out, the temperature goes down until the water hits 32 Fahrenheit, 0 Celsius, in which case taking the heat out doesn't lower its temperature. Instead, it causes a phase transformation. The liquid water freezes into ice. And until it's finished freezing, you basically can't drive its temperature much below 0 Celsius. Again, you get back the latent heat of melting, and you have to, that comes off and goes to the cold object. What else? I'll remind you about the activity that's taking place at the surface of the ice and the surface where the ice and water meet. There's a perpetual exchange of molecules from the solid to the liquid and from the liquid to the solid. They're going back and forth. And above 32 Fahrenheit, there's an imbalance in that landing-leaving process. Basically, above 32 Fahrenheit, that is when liquid water is more stable, water molecules leave the ice more often than they return to the ice, and so the ice shrinks. That is how melting occurs. Below 32 Fahrenheit, it's the other way around. The water molecules land on the ice more often than they leave, and eventually the water turns entirely into solid ice. right at 32 Fahrenheit, the landing and leaving can be in balance. And that's why those two phases can coexist indefinitely. All right. Any questions about freezing or melting of water, ice? Yeah, Victoria. How does water get to zero Celsius or 0 Fahrenheit? It's very high. It is possible to cool water below its freezing temperature, but it's not stable there, and it will do everything it can to turn into ice. I'll show you about an alternative to this, where basically a phase transition fails to occur. Actually, you may have seen this. There are hand warmers that are around that are reusable. There are a lot of disposal ones now in use, but there have been for decades hand warmers that contain a liquid. It's all in a transparent bag. I used to use this as a demo. I probably should bring it back someday. So they're a bag of a liquid, and when you press a little button and trigger something, it crystallizes. It turns into a solid. What that liquid is what's known as a supercooled liquid. It's below the temperature at which it should, by all rights, turn into a solid. If there's simultaneously solid and liquid present, the solid is hugely favored over the liquid at room temperature. And so it wants to solidify, but the liquid hasn't figured out how to crystallize. And until you give it a hint of how to form the crystals that are required for it to be a solid, it will stay in this liquid state even though it should by all rights be a solid. And you trigger it with a little button. You give it the hint that it needs to form a crystal, and it turns into a crystal. And as it does that, the attachment of the molecules to one another, it's not water, I think it's sodium acetate is the chemical in there. The attachments of the molecules to one another release their latent heat of melting. They're going from the liquid to the solid, and they bind more tightly to one another, in effect with weak chemical bonds, and that energy is released. It was released as thermal energy. It gets hot. So that was the classic hand warmer when I was a kid, basically. I mean, they're expensive, but they're really cool. And how do you it's reusable. How do you get it back? You heat it up to the point where the crystals melt. You put it basically in boiling water. The crystals melt. It becomes completely filled. The bag becomes completely filled with liquid. And then you cool it back to room temperature, and it has great difficulty figuring out how to, it's a chemical specifically chosen because it has trouble figuring out how to crystallize. And it becomes super cooled. That is, it's cooled below the temperature which it should become a solid. Is this familiar to anybody? Have you seen those kind of hand warmers anymore? They became kind of a specialty item maybe 20 years ago or 10 years ago when everything went disposable, the whole world. Nobody wants to reuse anything if they can. So. Oh well. All right, so that's the solid liquid and liquid solid phase transitions. Those are called melting and freezing. I've got 4 more to talk about. We've got the transformations between solid and liquid. Not surprisingly, we're going to come up with the transformations between liquid and gas, back and forth. And lastly, we're going to go between the transformations between solid and gas, which also exist. Okay. So, leaving, freezing, melting, and into the world of evaporating and condensing, which are the transformations back and forth between liquid and gas. It turns out that liquid water and gaseous water, which I'll call steam mostly, they can coexist over a very broad range of temperatures. And a reason why this can happen is because steam can have many different densities. You can have very dense steam, in which case the water molecules are packed tightly. They land on the liquid water very rapidly. Alternatively, you can have steam that's very diffuse, not dense, and the water molecules in that steam land on the water very rarely. So, at lower temperatures, if you want to have steam and water in phase equilibrium with each other, so that neither phase grows at the expense of the other, if it's cold, the water molecules are having a tough time leaving the liquid, gathering enough energy to break free of the liquid and become steam. So that the leaving rate is slow. How do you match that? Well, have the landing rate be slow. Well, how do you have a slow landing rate from steam onto liquid water? Make that steam very diffuse. not dense steam. Just a little bit of moisture molecules floating around above the steam as a gas. So in a cold situation, the phase equilibrium occurs when you have liquid water and just a little bit of moisture in the space above the water as a gas. The presence of air molecules doesn't make a whole lot of difference to this story. So you can think of it as just empty space with water molecules, or have the air in there too. So this explains why on a cold day, when you got water, a cold day, not freezing cold, but cool, really cool, even when there is liquid water around, it just rained, for example, there is not very much water in the air above it, because they're trying to go into phase equilibrium. The liquid water and the gaseous water are trying to balance. If they're out of balance, one of them will shrink to reach balance with the other. So you don't have very many water molecules in the air on a cool day, even when you're doing your best to make it as humid as possible. It's not very humid. Okay? I should say there's not a lot of humidity in the air. It may be as humid as it can get, and that does have consequences. It feels muggy, but it's not. The air is not very rich with water molecules. On a very hot day, though, that balance is struck with a different amount of water molecules up there in the gaseous state. The leaving rate now for water molecules from liquid water is ferocious on a 100-degree Fahrenheit day. Water molecules are breaking free all the time. They need energy to leave. That energy to leave is known as the latent heat of vaporization, but they break free easily because there's a lot of thermal energy around. So they break free all the time, and to replace them, you have to have water molecules land from the space, the gaseous form, all the time. So that needs to be a dense gas. So you have a lot of water molecules in the air on a hot day. All right? What do we get then? So my story here is, if the landing and leaving rates don't balance, though, one of the phases shrinks at the expense of the other. And you know these effects. Evaporation is the most familiar one. If you have water sitting around on a day when the water molecules in the space in the gas form they're not dense enough. They don't land often enough. The water will gradually disappear as more water molecules break free of the liquid than land on the liquid. The liquid shrinks. The gaseous water accumulates more molecules, and then that's evaporation. It requires energy for evaporation to occur, because the breaking free of the water molecules, which is taking place on average more than landing, requires that latent heat of vaporization. You have to pay the chemical, you're breaking weak chemical bonds, and they're not even that weak, pulling the water molecules apart and throwing one off into the space above the water. This is why evaporation is cooling. You know that if your hand is wet on a day where the air doesn't have enough moisture in it to prevent evaporation, the water gradually disappears and your hand feels cooled. What you're doing is, what's happening is, as the water evaporates, it's needing more and more thermal energy. It needs to be given thermal energy to break free additional water molecules and send them on their way in the gas, and so it's taking it out of you. So it sucks thermal energy out of you as heat, and you feel cold. You feel the loss of heat to that water, which in turn becomes a gas. Okay? The alternative to this is, suppose there are too many water molecules in the gas phase. It's too dense. So the landing rate is higher than the leaving rate. That is, water molecules land on liquid water more often than they leave the liquid water for the gas. You begin to accumulate more and more liquid. And that's known as condensation. You've seen this all the time too. This happens particularly when you take air that is really rich in water molecules, for having been drifted out of a hot shower, for example, into an area that's relatively cool, and it comes into proximity with some water. Well, this air now has too many water molecules in it compared to what it should have to be in phase equilibrium. So the water molecules land more often on the water that this comes into contact with this air, then leave the water to go back in the gas, and the water molecules accumulate. more and more and more. So you get mists appearing just right there in the middle of the air. Little droplets form right in the air, or they form on the mirrors, all that kind of stuff. Is this making sense? You okay with this? Ask me questions if not. You're rambling away. All right. Deep into the weekend. It's a long week. Okay. The latent heat evaporation plays an important role in this too. That when water evaporates, the energy that the water needs to break free molecule from molecule is actually kind of enormous. It's one of the highest latent heats of evaporation of any material in nature. Taking water from liquid to gas is very energy expensive. You have to put in an awful lot of thermal energy to rip the molecules apart and send them off on their way. Savannah? Well, the balance between liquid water and gaseous water has to do with two things, really. The temperature of the system, and as that temperature changes, the water molecules have different abilities to break free of the liquid. The colder you get, the harder it is for a water molecule to break free. So as temperature increases, the rate at which water molecules leave the surface increases. So that's part one. Part two is, so that's the leaving process. The landing process on the water depends on how dense those water molecules are in the space above the liquid. If there's only 2 of them here, they're not going to land very often. But if there are 1 million of them up there, they're just statistically going to land more often. So increasing the density of the steam increases the landing rate. So we've got sort of 2 different issues. The temperature adjusts the leaving rate from liquid to gas. The density of steam adjusts the landing rate from gas to liquid. And when those are in balance, nothing changes. But you can then see that, suppose you just take the system and do nothing else except raise the temperature. If that's all you do, you're not going to change the landing rate yet, because it's the same molecules up there. They're going to hit pretty much the same, with essentially the same rate. But you are going to break free water molecules more often from the liquid. So you will tend, that favors, just heating the system and nothing else, favors the evaporation of liquid water into gas. Alternately, if you increase the density, you just squeeze the gas together. Now you're increasing the landing rate. You're going to favor condensing the gas into liquid. Is that okay? So you can sort of figure out, for a given change, what's it going to do to the balance? Is it going to cause the water to evaporate or the gas to condense? Yeah? So if you take a frozen bottle of water out of a freezer and just put it on the counter and it looks like it has steam coming off of it, what you're doing then is you're taking a very cold object. So right out of the freezer, it's not 32 Fahrenheit, 0 Celsius. It's more like 0 Fahrenheit, which is minus, I don't know, about 20 Celsius. It's really cold. And the air that was around it was at room temperature, had something close to the right number of water molecules in it to be in equilibrium with water at room temperature. And now suddenly you're cold, you're reducing its temperature dramatically. And if that's all you do, think about it, you've got a system of air, and the only thing you do is just drop the temperature. Well, you're now shifting the balance between landing and leaving. Leaving is going to become rare. Landing is still present. So you're going to accumulate liquid water. And the steam that you're seeing is actually water droplets condensing in the air right around that really cold object. You're chilling the air. And the water that was already in the air no longer can stay as gas. It becomes liquid droplets. It's not actually water coming out of the bottle. Does that make sense? And you see that when you breathe into cold air in the winter. The moisture that was in your breath, which was roughly in balance between liquid water at body temperature and gaseous water, suddenly that same air is now dropped in temperature dramatically. The balance is struck now at a much lower density water vapor. And where's the other water go? It goes into liquid droplets. Clouds, same thing. Clouds can form out of seemingly nowhere. No, that was that was hot, moist air that was cooled to the point where the water came out of it, condensed out of it. Okay? Other questions? Okay, enough talking for a second. Just to show you the fun and games here. Got to do something other than just talk. So an example of this is, this can has a little bit of water in it. And right now, above the water is mostly air molecules, the conventional things, oxygen, nitrogen, that sort of thing, and a couple percent of water. But if I heat the whole system up, now I'm shifting the balance so that as that gets warmer, water molecules leave the liquid water more rapidly than before. It's the same gas above. Well, we're going to shift we'll go out of phase equilibrium into a situation where the water is evaporating to become gaseous water. And we'll get back to phase equilibrium at a higher temperature with denser water molecules in the gas. But then I'll add more heat, the temperature will go up more, and we'll be out of phase equilibrium again. Water molecules will go from liquid to gas. The steam will get still denser, still denser, still denser, and we'll get up to very dense steam. In fact, to the point where this contains no air molecules anymore, because the water molecules themselves are so dense that they can hold off atmospheric pressure and therefore fill the can. So the can won't actually have any air left. The air will have been chased out by water molecules that say basically, hey, you go away, us water molecules can do the job, or we water molecules can do the job. All right, so this will be all full of steam. There's boiling going on. There will be boiling going on, and that's another story that I'll come to in a minute. Boiling, it turns out, is nothing new. It is still evaporation. It's just a very aggressive form of evaporation. So water's evaporating more and more, getting denser and denser steam, and then I'm going to take the same system and drop its temperature dramatically. And when I do that, we're going to shift the balance back towards low-density steam and cold liquid water. They're stable, and the can itself will just be crushed because it won't contain any air anymore. It will contain a very dilute gas of steam, and that won't be enough to stave off atmospheric pressure. So the trick is to flip this guy upside down. Do you understand what just happened? When I put the can into that bath of cold water, the temperature just plummeted. The balance between steam and liquid water shifted abruptly from dense steam, hot liquid water, to cold liquid water and steam that was way too dense for being cold. And the steam condensed like crazy and basically just stopped being a gas. So the can was abruptly almost empty of gas. The number of gas molecules in it plummeted by a factor of to maybe 5% of what it was before I flipped this guy over. So suddenly it only had enough gas molecules in to produce 1/10 of atmospheric pressure or 1/20 of atmospheric pressure. Well, now you've got a pressure imbalance. This is sort of a rich story. It goes all into the world of pressures, right? The pressure inside the can was almost zero. The pressure outside the can was still atmospheric. That's a terrible pressure imbalance, and the can crushes. Actually, people in this department have done this sort of demonstration with a 55-gallon drum. You heat water inside the 55-gallon drum until the drum fills with steam only, no air. You seal it and put it in the side of the room, and then you wait. You turn off the heat and wait. And it crumples very abruptly after about 10 minutes. So it's one of those kind of demonstrations that it puts everybody on edge for 10 minutes. I can't stand it myself for that very reason. It's like the balloon exploding demonstrations that, like, where's it gonna go? Okay, so this guy is pretty much filled with steam at this point, and I'll just pick it upside down and crush away. All right? Yeah. Is the can sealed at the top? Actually, we never really seal the can. Sealing the can is always a bad idea when you heat it, because as you build up the density of the steam, the more you heat it, the higher the density of the steam goes. you can make the steam more dense than it needs to be at atmospheric pressure. You can drive the pressure, the density and pressure higher and higher. You can blow the can up by a true explosion. This is why sealed containers with liquid in them, it's not a good idea to put those in a fire. They tell you, like the aerosol bottle, never put it in the fire. It's because you will turn a liquid into a gas by shifting the balance between liquid and gas, and the gas will get denser and denser and more pressure, until finally the can can't tolerate it. Kablooey. Yeah. Yeah. Before I heated it up, it was in phase equilibrium. There was liquid water in it. There was gaseous water. Neither phase was changing much. You know, they're not quite perfectly in phase equilibrium, probably because the can was open at the top. So a little bit of water was sneaking away or sneaking in. We don't know. It was pretty close to phase equilibrium. Then I shifted the temperature up. Now it was definitely out of phase equilibrium. It was too hot, and water molecules were going from liquid to gas very fast. Until we reached, maybe by the time I took it off, we were at a new phase equilibrium. But as soon as I put it in, I flipped it upside down. I never sealed it, but flipping it upside down puts water in contact with the open mouth of the can. And the pressure inside the can drops so precipitously when it cools down that the pressure plummets in the can. There isn't time for water, which is pretty viscous, to flow in and fill the can and make up for the fact that the can is no longer filled with very much. It tries, but it fails. So the can is crushed by the surrounding air before the water can get in there and take the place that the gas left. Yeah. So the question is whether the story is that I'm heating it and the density is increasing, or that heating it increases the leaving rate, I call it. Those are the same story. So that heating the water up, means that water molecules break free from the surface at a more rapid rate than before. The consequence of that more rapid leaving is an accumulation of more water molecules in the gas phase. So the density of the gas, the gas goes up. So I guess one's cause and one's effect. Yeah. Yes. So the question is the amount of steam leaving the can is negligible? Pretty much. It just doesn't matter much. It would be possible to heat this essentially with the can covered. The pressure would build up. That's dangerous. Leaving the can open so the steam can go out just means that, well, we'll get a certain amount of steam in there. If we drive more steam into the gas phase, instead of accumulating yet higher density, some of it will go out because it's reached, it's become in excess of atmospheric pressure. Now it pushes itself out the mouth. So there's some details here that, well, yeah, they're making it more complicated, but they turn out not to be very important. And this is a pretty reliable scheme. We made a system that was almost in phase equilibrium at high temperature, where the water vapor was so dense it was essentially at atmospheric pressure all by itself. It didn't need the help of air to maintain atmospheric pressure. Yeah, Julie. Yes, so just before I immersed the thing in cold water, what did the system look like? It was basically liquid water that was very hot and gaseous water that was very dense. And water molecules were very rapidly leaving the water for the gas, but also landing from this dense gas on the water, and they were pretty much in equilibrium. But now it's a different equilibrium than we had earlier at low temperature. When I picked it up and flopped it over, I took it out of equilibrium very quickly. It went from being hot water and dense gas to cold water and dense gas. Uh-oh, that's not stable. The dense gas now is still landing like crazy on the cold water, but the cold water isn't replacing it. They're not taking off. Water molecules aren't breaking free of the liquid very, very rapidly anymore. So suddenly, what was a balanced system becomes unbalanced in favor of turning the gas into a liquid. And that liquid condenses like crazy. The water molecules land 100 times faster than they take off. They're gone. They just disappear from the gas. And the pressure of that gas, along with its density plummets along with its pressure, and the surrounding air just crushes the can. Anything else? Okay. So just sort of the summaries of how to make water evaporate. To make water evaporate, you want to make sure that the landing rate from the gas is slower than the leaving rate from the liquid. And there are ways to do that. Adding heat does that. Reducing the density of the steam, basically making it rarer for water molecules to land, causes evaporation. Condensing steam, you do the reverse. Take heat out of it, or you make the steam excessively dense so it lands too often and the water accumulates. And there's then that latent heat of evaporation that I talked about. Or technically, it's known as the latent heat of vaporization, but I prefer to call it evaporation because it's just more familiar. All right. So what about boiling water? Is that a different phase transition than evaporation or condensation? It turns out that boiling is just a glorified version of evaporation. When you heat water, so I guess I can zoom in on this. Remind me when we're done to unzoom. So I will heat some water. There you go. I don't know whether you can see it. The condensation formed on the beaker the instant I triggered the burner. Did you see that? It's gone now. What that was the burning of, this is natural gas, but the burning of methane. The main chemical product of the combustion is water molecules. And those water molecules, so the gas produced by in the flame is really rich in water molecules. And on a cold surface, which this was briefly, the water molecules were landing more rapidly than they were taking off, and the water condensed. So there was a brief period when the beaker was covered with water droplets. And now they're gone because the temperature started to rise. Anyhow, what's going on right now is water molecules are leaving the top surface at a certain rate, and that rate's getting faster and faster as the water gets hotter. They're landing on that surface at a rate that's determined by the moisture in the air. And the rate is definitely, the landing rate, I can tell you, is slower than the leaving rate, and the balance is getting more and more out of whack. The water molecules are breaking free more and more frequently. They're still landing at the same rate because the same air is overhead. So we're going to gradually start evaporating water at a faster and faster rate. It was already evaporating before I lit the fire. It's evaporating faster and faster, but that evaporation is taking place entirely on the top surface of the beaker. It can't take place from the side because there's no surface out of which to go. So that's just ordinary evaporation. As the water's getting hotter, and this came up the other day, it starts to form bubbles. You can see little bubbles. I can see them. I don't know whether you can see them. On the inner surfaces of the beaker. Those are not steam bubbles. Those are bubbles of ordinary air that used to be dissolved in the water. There are also probably there may be bubbles of chlorine, other things they put in the water to keep it sanitary. But those bubbles come out of solution because it turns out that most gases become more soluble at low temperature. So as you heat up the gas, as you heat up the water can't stay in solution the gas can't stay in solution as water as easily, and it comes out of solution as bubbles. And you've seen that in pots. As you heat up water in a pot, these bubbles appear on the surface of the pot as the water gets hotter. We're getting close. Some of the bubbles are breaking free and floating up, but we're still not at boiling. What's going to happen eventually is, and you've seen this all your life, the water will begin to boil. So what's boiling? Well, as the water comes off more and more aggressively off of any surface in here, the density of water vapor, if I trap the water vapor above it, that water vapor becomes denser and denser, and therefore its pressure becomes larger and larger. So suppose that we make a little empty spot in the middle of the water. I don't know how, we just temporarily open up an empty spot in that water and allow water molecules to move between the liquid water on the outside of this bubble and the gas inside the bubble. So now there's a new piece of surface, that bubble-shaped void inside the water, and the water molecules can leave the liquid for the gas in the bubble, or land from the gas in the bubble on the liquid, back and forth. Well, at lower temperatures, the bubble, if the bubble only has water vapor in it, no air, the density of water vapor that at phase equilibrium between, where the water is leaving and landing at the same rate, the density of water vapor in that bubble will be pretty low, and therefore its pressure will be pretty low. The bubble will be a low pressure bubble, and it's not by itself, unfortunately it's surrounded by atmospheric pressure air, the whole container is, and that bubble will get crushed, just smashed out of existence. It tried to appear, I'm trying to make this story sound, it's trying to be there in existence, this bubble of steam, but the steam that is in phase equilibrium with cold water is too low in density and therefore too low in pressure. The bubble can't tolerate the crush of atmospheric pressure and it gets smashed. Questions about that idea? I hope it's followable. But as the temperature goes higher and higher, the density of steam that is in equilibrium with liquid water at hot temperatures it's much more dense, and the pressure is higher. And at a certain temperature, 212 Fahrenheit or 100 Celsius, the density of gaseous water that is in phase equilibrium with liquid water is atmospheric pressure. It's dense enough that it has atmospheric pressure. So the bubbles, and now it's starting to boil. What you're seeing then is bubbles of pure steam that have such dense steam inside them. It's in phase equilibrium with the water, but the steam is so dense that it has atmospheric pressure. And it is therefore able to keep from being crushed. And once it forms like that and is stable against the crush of atmospheric pressure, it can actually grow by evaporation. So the bubble starts small, and then more water molecules evaporate into that bubble, and instead of the density going up, density and pressure go up, it expands. And then more water molecules can evaporate into it, and more. So what you're seeing now is evaporation, just good old-fashioned evaporation, where the water molecules are leaving the surface of liquid water for gaseous water, but it's taking place not just at the top surface anymore. It's taking place throughout the liquid by evaporating into the bubbles. They're growing by evaporation, and they're stable against the crush of atmospheric pressure because they're very dense. And they're dense because they're hot. The water is so hot that it's able to fill them fast and make them dense. Questions about that? It's a lot to take in. Yeah. Are these evaporation bubbles different from the gaseous bubbles that were in there originally? Yes. They may have started as one of those bubbles of like nitrogen and oxygen. But evaporation occurred into one of those bubbles. It became substantially water molecules in the bubble rather than just the original nitrogen and oxygen. And by the time the bubble gets this big, it's got only a tiny fraction now of air. But the air bubbles are a lovely place for the bubble to start. The bubbles, it turns out, need somewhere to start. It's a process called nucleation that. And so I can ask this question: can liquid water ever be heated above its boiling temperature? And I should say that once you hit boiling like this, evaporation is so aggressive, there's so much surface available, that it's hard to drive the temperature of this water up very high above its current temperature, because most of the heat that you put into it now goes into turning liquid water into gaseous water, not into raising the temperature of the water. You can get it a little above 100 Celsius, but not easily. It's just a huge sink of heat to turn liquid water into gaseous water. And it's got so many ways to do it now with all those bubbles. So where I'm headed, thanks. We can stop looking at that. So the question I can ask you here is, can you ever heat water above its boiling temperature? I'm telling you that when it's boiling, it's really tough, because the water soaks up all the heat you pour into it and uses that heat to create new gaseous water out of the liquid. But can you get around this somehow? So how many think yes? How many think yeah? How many think no? You can't get around it. Okay, so it's a few voters, about mixed choices. I'll stop this because otherwise we're just turning liquid water into gaseous water, basically at a pretty well fixed temperature of 100 Celsius. Incidentally, when you cook with boiling water, what you're doing to an extent is you're using this natural tendency of water to hit 100 degrees Celsius, begin boiling, and then have a terrible time going above 100 degrees Celsius, which is 212 Fahrenheit. You're cooking that in an environment with a well-defined temperature. So when you boil an egg, what you're doing is you're exposing the egg to a temperature that's very well defined, almost exactly 212 degrees Fahrenheit. And it cooks at a certain speed as a result. It's not the boiling water that's interesting, it's the well-defined temperature that's interesting. Anyhow, so having said, ask this question, can you ever heat water up? And the answer, as you'll see in a moment, is yes. And the way in which you do this is don't allow the boiling to get started. It turns out that boiling doesn't always start when you hit 100 degrees Celsius, because this whole idea of water evaporating into bubbles assumes the bubble is there in the first place. If there is a bubble and the temperature is 212 degrees or above, the water can evaporate into that bubble and make the bubble grow even though it's got atmospheric pressure around it. If the bubble exists and the temperature is below 212 degrees Fahrenheit, that bubble is going to shrink. It's not going to get bigger. In fact, it's going to get smaller and disappear. But what if there's no bubble to begin with? So this is a video from a while back. Where's the sound? How do I get the sound on this? Is there a mute? Oh, come on.
On something that you use every day, probably without thinking about it, the microwave. Tonight, we're going to show you how it can cause a dangerous explosion in your kitchen. This is actually a story suggested to us by one of you in a letter over the internet. And it involves a bizarre phenomenon. Before you use your microwave again, you really ought to see what Chris Cuomo found in this primetime owner's manual.
At about this time last year, Patty and Dave Long of Naperville, Illinois, were preparing for Easter.
It was Good Friday. The kids were off school.
Time to make Jell-O Easter eggs. Patty put the water in the microwave for 3 minutes to boil, but something seemed wrong. No bubbles.
So I hit the add 30 seconds, and I stood and watched it. But it wasn't boiling, and I thought, well, it's got to be boiling. Something has to be wrong.
Patty had been using a microwave for years. She was confused.
So I opened it up, I brought the container out, and I just kind of brought it down like this. So I was going to touch it with my right hand, and before I got my right hand there, I heard this like whoosh, and I got hit with all that water into my face.
It exploded.
It exploded like a bullet, and it just hit the ceiling too. There was no water left in the cup.
Patty had first and second degree burns all over her face. Even worse, the corneas of her eyes had been scalded.
The whole eye was burned, and they were swollen on the inside, so it was blocking some of the vision because of the swelling inside the eye from the heat.
Were you afraid that you may have gone blind?
Yeah, I was afraid I'd never see my kids again.
It would take 6 months of treatment for Patty to fully recover her sight. Still, no one could explain what had caused this accident.
It really wasn't until I got home and saw the water on the ceiling that I really understood that something strange had gone on here, something that I'd certainly never heard of before.
People who have these sorts of accidents are probably reluctant to talk about them because it seems so bizarre and so unlikely. Who would ever expect water,
I didn't always have
the
gray
safest
hair.
thing we can imagine, to come up and hurt us?
Let us show you what happens in slow motion. Water heated past boiling, more than 212 degrees, can erupt. Marianne Ostermeyer says it happened to her, too. A middle school teacher in Southern California, she'd been using a microwave oven for nearly 20 years. She says she had been cooking homemade soup on low power for 50 minutes. Remember, low power.
Well, I ended up grabbing 2 hot pads. I opened up the microwave. I had one on the handle. I took and poured a small amount of soup in the cup. Then I reached in to the utensil drawer. I picked up a fork. By this time it was sitting down. I took the edge of the fork, or the tip of the fork, put it in, and the next thing I knew, there was this incredible sound like a gunshot or a backfiring of a car. And immediately there was an explosion. I mean, the whole thing just exploded.
What was the extent of the injuries?
First-degree burns on the face, first-degree burns on the wrist, and on the top section of the chest region. First degree, the lower quadrant of the left breast, third-degree burns.
Third-degree burns.
Yeah.
Both Marianne Ostermeyer and Patty Long's husband, David, searched for answers and found them here, a website by University of Virginia physicist Louis Bloomfield. It features video of an experiment that looked painfully familiar.
I probably get more questions about microwave ovens than all the other questions I get combined.
Professor Bloomfield says there's a simple scientific explanation for how these kinds of explosions can happen.
You're used to having water or liquid boil when you heat it above a certain temperature. But there are occasions, and they're more frequent than you'd expect, in a microwave oven where the water goes to or above boiling without any bubbles forming. That's a phenomenon known as superheating.
Superheating.
Yeah, it's hotter than it should be for normal boiling to occur, and yet it doesn't boil.
Here's why. Something has to start the bubbles forming. Any little imperfection, like the texture of a metal pot, will do.
But in a clean glass container, heated by a microwave, there's really nothing to trigger the bubble formation. It's a process that physicists call nucleation. That bubble formation never starts.
So Bloomfield says, even though it may look unheated, it can actually be superheated.
Now, what does that mean exactly if water's superheated? It's just hot? How's that dangerous?
Well, it's almost like a bomb once you've got it superheated adequately, because anything that triggers the boiling, once you've reached that temperature, will cause catastrophic, very sudden flash boiling.
Now, can you test this? Can we show it?
Well, we've got a container of about half a cup of water here with some red food dye in it and a little bit of fat floating on the surface, a little oil.
Like it were soup.
We microwave the liquid on high power for about 3 minutes. There isn't a flash reaction every time, but this can be dangerous. Don't try it at home. Look what happened to us.
Ready? Let's go.
Bloomfield says all it can take to trigger an explosion of superheated liquid is for something like a fork to break the surface. Then, watch out.
So, yeah, that was some time ago, but for a while I was sort of like the world's expert on superheated water. I got dangerous, and I finally had to stop. We were filming in my house with a Washington news crew at some point, and I had gotten so good at superheating water. Basically, the issue is you want to make sure that there are no bubble nurseries, nothing there to initiate the first bubble, and I learned how to sort of kill them all off, so there'd be no nucleation. So we were filming with the microwave closed, and I took it to boiling, and then just a little bit of water, and I cooked it I set the timer for 30 more seconds, and they've got their camera in there real close, on high frame rate, fast shutter to watch this whole thing. I'm over there hovering along, watching it, and at 29 seconds, had it gone to 30, I would have opened it up and stabbed it. But at 29 seconds, it went on its own. It did not wait for me to stab at it and break the surface and introduce the first bubble. And in a single frame, you watch later, it went from liquid in the container, door closed, to no liquid in the container, door nowhere in sight because it had just hit me in the head, and me going, wow! That's I think that was the last superheated experiment I did. But the point of this is you actually have all seen this happen yourselves. When you make coffee or tea or something like that in the microwave, and you pull it out and you put something in like the tea bag or like sweetener or something like that, and you see the amusing bubbling, and maybe a little bit splashes out. This has surely happened to some of you. That was mildly superheated. That is, it's hotter than boiling, but it doesn't have any way to make the first bubble. Seriously superheated water is possible. It's not easy to do it, but it does happen from time to time just by chance. And do be a little careful with water. It's the smoothness of a glass container and the evenness of microwave heating that really makes it possible. Anyway, that's all for today, and see you on Monday.